Let's start.
This call is now being recorded.
Welcome everyone. In this lecture, we shall discuss the temperature effects of on the PN junction diode, on the various parameters of the PN junction diode, and how those parameters are affected by the temperature. We will discuss. And before that, let us finish our discussion on the diode models. So, in the previous class, we learned about the diode models. We have seen there are three kinds of diode models. Number one is ideal diode model. Number two is ideal diode plus voltage source model, and this is also called the constant voltage source model. Third one is the ideal diode plus voltage source plus resistor, which is also called the piecewise linear. So we discussed these three types of model in the previous lecture, and how we can model in these models. In ideal diode model, we model the diode as a open circuit when diode is off or not conducting, or the current is zero, voltage across the diode is less than zero, and we model the diode as on or conducting when ID is greater than 0. And in ideal diode model, we model the diode with the help of one constant voltage source and ideal diode. So this is the ideal diode plus constant voltage source model. And in the third type of model, we have modeled the diode with a small resistance RF and ideal diode. Now, uh, in order to understand these models separately, let us try to solve the same numerical which we have solved with the help of ideal diode model. So that will give you more clarity about these models. How can we apply these models on the circuits? And definitely, and the systematic solution of diode circuits we will learn after the temperature effects. And in that topic, we will learn the state assumption method, a generalized approach to solve all the diode circuits. How can we solve a diode circuit with the help of state assumption method? That we will learn in the subsequent lecture. Okay. So the problem was this: we have a 10-volt source, a 5-volt source, and there is a diode, a resistor there, and this is a 5-volt source. Let us assume this resistor is R. And okay, for the there is one more problem where this battery is reversed. So in the ideal diode model, we applied the ideal diode model on this diode, and we saw how can we calculate the current. And if this polarity is 5 volt here, the positive potential is connected to the p side, then definitely this diode will be forward bias, and we can say this will be conducting. And if this diode is conducting, then we can then we replace this diode with the short circuit here in the ideal diode model, and then we try to calculate the current, which is the 5 by r. So this we have already done in the ideal diode model. Similarly, for this voltage, we are applying negative at the p side of the diode at the and one more thing, these P and A is also called anode and cathode. Okay, anode and cathode also called this. This side P is called anode and C is also called cathode. In some so in some literature you can find this anode and cathode. Okay, so this is the 5 volt diode, and now in the ideal diode model, this was reverse bias, and we replaced this diode with the off with the open circuit, and then we try to calculate the voltage across the open circuited diode, and we use the KVL. Okay, now we shall again try to solve this problem with the help of other two models. So first we will use the constant voltage source model. This model, this we have already done in the previous lecture, and now we shall try to solve this problem with the help of this constant voltage source model. So in order to solve this diode with the help of this constant voltage source model, so first we will replace this diode with the voltage source and idle diode. Now this is VF, and we know that if my diode is silicon, let us suppose my diode is silicon or germanium, and this will be given in the problem. So this is how we can replace the diode VF here. We can This is how we can replace the diode VF. Sorry, diode with VF and idle diode. Here we have replaced our diode with the constant voltage source, and again the same thing we will do here. This is VF and this is idle diode. Now again we will try to do the analysis for this problem and for this problem. Now what will happen? This is the voltage 5 volt, and this is these both voltages are opposing each other. Here you can see these both voltages are opposing each other, and and now you can see this 5 minus Vf is applied at the at the p side of the diode, at the anode of the diode, this 5 minus Vf, and we know that this Vf is not greater than 5. For a germanium diode is zero point 0.3, and for the silicon diode is zero point 0.7, and for any other diode is between well, zero point 0.3 to 2. So definitely this voltage is not greater than this voltage. So a positive voltage will be applied here. Okay. So if this positive voltage will be applied here, then this diode will be on, and we can replace this diode. We can replace this diode by short circuit, because this is on, and this is our idle diode. We know that this is the idle diode. So now we are doing the analysis for idle diode, and now we can calculate the current. So definitely if the I current is flowing in this diode ID, then this ID will be this voltage 5 minus Vf over R. So now you can see in the previous case the ID was 5 upon R. In the previous case the ID was 5 upon R. But here you can see this ID is 5 minus Vf upon R. So the value of ID is decreased. Okay. Similarly, we can solve the problem, this problem, and if we are applying the idle diode model here, and you can see here this voltage and this voltage are supporting each other. So there will be more negative 5 plus Vf. The negative of this and this voltage will be added. We know that these voltage source will be added because they are in same direction. So you can see here the polarity is similar. So here the negative voltage 5 plus Vf, negative minus 5 plus Vf is applied, and you can see we have applied a negative potential on the P side of the diode. Then the diode will be off. So we will replace the diode here with the open circuit. With the open circuit we will replace, and let us suppose the voltage is Vd. Now we will try to calculate the Vd with the help of KVL. So here this is 5, and this is also positive to negative. Vf plus Vd. Let us suppose the current is flowing in this direction, and this Vr, even though there is no current flowing, we know that this is open circuited. So 5 plus V, as the no current is flowing, so there will be no drop across this resistor. So this VR will be 0, and we can solve this further. So 5 plus VF plus PD equal to 0, and this VD will be minus 5 plus VF. So the now you can see the negative voltage on the diode is increased by Vf. Okay, so this negative voltage is increased. So this here we have applied the constant voltage source model, or the idle diode plus voltage source model. And now again we will apply the third model on the same problem. So this will make everything very clear. So again, if we replace the diode, because let us suppose there is a diode, then definitely we will add one more resistor here and one more resistor here. In the third model, you can see we will replace our our diode with the voltage source, a small resistor RF, and one idle diode. Again, we will analyze the situation. Here we have replaced the diode which was present in our circuit with the VF and a resistor RF having a small value, and this value will be given in the numerical if it is asked in some question. Okay, so now again we will try to do some analysis. So again, if we see this polarity, we'll try to make this diode forward bias. This will push the diode in forward bias by raising the potential at the P side. And if it is raising the potential at the P side, then definitely it is pushing the diode to the conducting mode, and the diode will conduct. And if the diode will conduct, we will replace the diode with the short circuit because it is an idle diode. Okay, and here again this battery will try to decrease will try to lower the potential at the P side. So it will increase the barrier. So the diode will again diode will be off. The diode will be blocking the mode. So the diode will block. So we will replace this diode, this uh, this idle diode with the open circuit VD. Now again we will try to calculate the ID. Here you can see the potential will be 5 minus RF, but the resistance will be added because these both are in series. These resistance are in series. So this RF is added. Okay. So here you will see the current will more decrease. This ID will more decrease because already in the previous expression it was decrease 5 minus VF, the numerator was decreased, and here in this expression the numerator is already decreased in the previous expression, but the denominator is increased. So if the numerator is decreased, denominator is increased, then definitely the value of fraction will decrease. So just by the simple mathematics, you can calculate. This is just by the KVL, okay? And again, let us apply the KVL here. And here you can see this RF and R. Again, this is the combination. So if 5 plus VF plus VD, voltage across this small RF, and this voltage across this small VR, and we know that voltage across this RF and VR will be zero because there is no current flowing. So the voltage across the diode is minus 5 plus, which is not changed here. Okay. So this is how you can analyze the circuits with the diode. This is just a simple circuit. When we are using more than one diode in the circuit, then the circuit will be complex, and for that for those circuits we will learn a state assumption method in the next class. Tomorrow we will learn the state assumption method in order to solve the diode circuits, and then we will come to the rectifiers, the most important application of the diode. There are three kinds of rectifier in our syllabus. We will finish the rectifiers, and then the filters, and with that the unit 2 will be finished. And there are some small topics like transition capacitance, diffusion capacitance, and avalanche and Zener breakdown and Zener diode. And we will finish them in time before your exam, and those topics are very easy, and for some topics I will provide you notes which are very good. And if you have any doubts, then you can ask me tomorrow 11 a.m. There will be a doubt clearing session, live interaction, so in that session you can ask any doubts. Okay, now we will come to the temperature effects, the next topic, which is entirely different from this, that is the temperature effects. Temperature effects on PN junction. We know that this is the characteristics of the PN junction. This is the current ID in milliampere. This is ID in microampere, and this is VD, bias voltage. And if we try to draw the characteristics, then characteristics is like this. If we try to draw the characteristics, this is like this. It's almost like 0 to some. Actually, initially it's not visible, then suddenly it goes very high. There's one more thing that you need to understand in that modeling. In the modeling that we have done for the diodes, we have done the modeling for the diodes. Um, in the there are three kinds of modeling we have done for the diodes. So in the modeling of diodes, we are doing the modeling for forward bias region and this reverse bias region. Okay, so actually I have already discussed with you that there are three parts in the diode characteristics. One is the forward bias, one is the reverse bias, and one is the breakdown. So this breakdown is not modeled. We have not modeled the breakdown region because in the general purpose diode we are operating them in the reverse bias or forward bias, and there are some special diodes like Zener diodes and other diodes which we designed to operate in the breakdown region. So we do not use them in the breakdown or in the reverse bias region or forward bias region. We use them in the breakdown region. And the circuit and the analysis of the Zener diode we will do separately. So in the modeling, the modeling of the diode we are doing for the forward bias region and reverse bias region only. Okay, so remember this. So this is the uh, characteristics. This is the forward voltage drop, which is almost 0.7 volt. Okay, for the silicon diode and for the this is the breakdown region. Now we will try to understand the temperature effect. So one thing that we need to understand the the one temperature the temperature dependence of here we will try to understand the temperature dependence on the two parameters, one in forward bias, one in reverse bias. In the reverse bias our parameter will be reverse saturation current, and in forward bias our parameter will be forward voltage drop. So we will try to understand the temperature dependence of these two parameters. What is so by this I mean, if the temperature will change, then what will happen to this voltage? And if the temperature will increase or decrease, what will happen to this voltage? Okay. So this is experimentally observed. Okay. So what we need to understand, if we are increasing, if definitely if we are increasing the temperature, and let us talk about the reverse saturation current first. So as we know, if we are increasing the temperature, then we will increase the number of intrinsic carriers, and which are the minority carriers on the p side, and the minority carriers at the n side. Definitely, if we increase the temperature of a p-n junction, what will happen? The minority carrier will increase, as the intrinsic minority carriers are dependent on temperature. So the concentration of intrinsic concentration is a function of temperature. As the temperature will increase, the intrinsic concentration will increase. So the p side, at the p side and n side, the minority carriers will increase. And we know that this reverse saturation current is the drift current, in the reverse bias region. So if this if the minority carriers will increase, then definitely this drift current will increase. So you need to understand that if the temperature will increase, then definitely this reverse saturation current. The terminology is reverse saturation current. This is the reverse saturation current. If the temperature will increase, then this reverse saturation current will increase. So how this reverse saturation current will increase for the silicon diode? Here we will try to understand. So there is an observation. This is practically observed, and whatever I am telling you is practically observed in the laboratories with the experimentation. So that's why you will have to accept those facts, and for the cross checking you can use the internet. Okay, so we will try to understand this reverse saturation current is a function of temperature. So by this we can because the intrinsic concentration of a semiconductor will increase when the temperature will increase, and we know that this reverse saturation current is the drift current. This we have understood in the reverse biasing of a p-n junction. So if this reverse saturation current will increase as we increase the temperature, then what will happen? Uh, so then there must be some kind of relationship. So here we are trying to understand that relationship. So you must understand, in the reverse bias region, the reverse saturation current of a silicon diode doubles for every 10 degrees Celsius rise in temperature. So it doubles for every 10 degrees Celsius rise in temperature. So this is the practical observation which is related to the reverse saturation current. So as we have concluded here that this reverse saturation current is a function of time. So it doubles for every 10 degrees Celsius rise in temperature. So what you need to understand this, if let us take some example in order to make it more clear. So if at some certain temperature I naught is 20 microampere, because this reverse saturation current is of order of microampere. If for some particular temperature at T equal to 25 degrees Celsius, let us suppose at a temperature of T equal to 25 degrees Celsius, it is 20 microampere. Then the relationship is like this: it doubles for every 10 degrees Celsius rise in temperature. So what will be the value at 35 degrees Celsius? Double. I naught will be 40 microampere, and it is at 35 degrees Celsius it is for 40 microampere, and for the current having for the temperature at the 45 degrees Celsius we will have 80 microampere. So this is like this. So let me create you a mathematical expression for this thing. Okay. So this you can find. You can find here that if the temperature rise is very high, let us suppose this is to 25 degrees Celsius, and I need to calculate the current at 125 degrees Celsius. Then what will happen? Then I will have to go on like this. So instead of going on like this, we use a expression, mathematical expression for this, and this expression is particularly for the silicon diode. We are studying this silicon diode here because the statement is it doubles for every 10 degrees Celsius, right? So there is a mathematical relationship that we can write. If we want to calculate the current at a temperature T2, then we need to write the current at temperature T1, the given 25 degrees Celsius पे जो current की value 20 microampere, and then this current doubles, so we will use 2, and then T2 minus T1 upon 10. Why 10? Because for every 10 degrees Celsius rise it increases. For every 10 degrees Celsius rise it increases. So this is the expression that you should understand. And this expression might change for the situation. If situation is like this, that for some other semiconductor at 8 degrees Celsius, it doubles, then this expression will change. Here, this 10 will be replaced by 8, or this might also change to value. It is double at sometimes it is 2.5 times, it is 3, so it is thrice. So it is just the conditional here. Just by looking at the statement, I have derived a mathematical formula for me. So you can apply the formula for this numerical. You can see I am raising the temperature to 25 to 45. This 45 minus 25, it will be 20, 10, and 10, 2 raised to the power 2, 4, 4 multiplied by 20, you will get the 80 microampere. So this you can apply, and this is a mathematical expression for this. And one thing that you need to understand, so if you see this thing as a characteristics, so if you increase the temperature, then this characteristics will be changed. Like if you are increasing temperature, so we are increasing temperature, then this characteristics will be changed like this. Okay, now quickly we will try to understand the, the temperature dependence of the forward voltage drop. So it is particularly observed whenever we increase the temperature, the forward voltage drop of the silicon diode decreases by minus 2.5 millivolt per degree Celsius. One more thing that you need to understand, the here I have written the statement, it doubles for every 10 degrees Celsius. Okay, for the silicon diode. And one more mathematical way of expressing this statement will be that the current increases by 7% for every 1 degree Celsius rise in temperature. So these both statements are equivalent mathematically. So if I am saying it doubles for every 10 degrees Celsius rise of the temperature, or if someone is saying it increased by 7% for every 1 degree Celsius rise in temperature. So if you are not convinced with me, then use mathematics and try to find this, increase the current, assume the current x and increase it by 7% for every 1 degree Celsius, and then if you try to find it till the 10 degrees Celsius, you will get the double cut. Okay, so here for the forward voltage drop, what will happen, the forward voltage will change, will decrease minus 2.5 millivolt per degree Celsius. So if I increase the temperature, then the characteristics will be like this. Here I will, if I am increasing the temperature, or if you decrease the temperature, if you then this effect is reversible. So then this will reversible means, and definitely this is minus here. So whenever we increase the temperature, then this value will decrease, because it is minus 2.5 millivolt per degree Celsius. And if we decrease the temperature, then definitely the characteristic will shift to our right. So here we are decreasing the temperature. So you need to understand this is the characteristic. And you can solve one numerical problem, very simple numerical problem. Let us suppose we have a forward voltage drop of 0.75 volt. Forward voltage drop of 0.75 volt at some temperature of 30 degrees Celsius. And I need to calculate the forward voltage drop and if the temperature is increased to, let us suppose 30 is 130 degrees Celsius. Okay. Now temperature is increased, and if the temperature is increased by, so what you need to understand, this diode might be at some industrial condition, okay, at some place where the temperature might increase. So it's not like that you are learning the diode. So the experimentations, whatever you are doing in the experiment in the lab, that is at the NTP, okay. But most of the time we use the circuits in which we use the diodes, and we use the circuits for the control in the industry. So there might be a temperature rise of 130 degrees Celsius. So the temperature is rise by 100 degrees Celsius. So this will decrease. Definitely temperature is rising, then this will decrease. And we know that for every degree Celsius, it is rises by one. It is decreased by minus 2.5 volt. Okay. So we will multiply this. So you will get 25 millivolt, not 25 millivolt, 250 millivolt. Okay, 250 millivolt means 0.25 volt. So the temperature, so this forward drop will decrease by 0.25 volt. So the new drop will be 0.5. Like if this is like this, so here 0.5. So the new forward voltage drop will be 0.50. So these are the temperature effects or the temperature dependence on the PN junction parameters. So we have understood the temperature effect on the reverse saturation current and on the uh, forward forward voltage drop of the diode. So here we are concluding this session, and in the next session we will discuss some numericals related to the diode equation, and we will try to understand the state assumption method. And for there is one more topic which is called the load line analysis. I will provide notes for this load line analysis because this is just a graphical method of solving the circuit with the help of diode. What you need to understand about this load line analysis, let me give you some idea about this load line analysis. That we know that there is a characteristics of a diode, and if a diode is placed in some circuit like this, and I want to find the solutions on the basis of this graphical method. Okay, so this is a graphical method of finding the solution. So by using this battery and resistor, I can find, because this is a linear element, this is a linear, so there will be a, I can find some line here, and this will be the solution. Okay, so this is how you can obtain the solution for the circuit, because the characteristics is non-linear. We know that this characteristic is known to us, and with this known characteristics we will try to find the operating point. It means the current flowing through the diode and the voltage across the diode. So with the help of these elements we will try to draw the other line, and we have learned this basics in the 10th class or in the ninth class, that we can find the solutions of the linear equations with the help of graphs, and we just plot them, and at the point where they are meeting, so that will be the solution. So similarly, we have a non-ideal characteristics which is known to us, and with the help of other elements we can plot the other uh, characteristics, and the point at which these two curves meet will be the solution for our circuit. So for this load line analysis, I will provide the notes, and if these notes are not sufficient, then let me know. Then definitely we will cover this in the session. Okay, so here we are concluding. So stop the recording now.